In the early 2020s, returning humans to the moon felt like a clear, linear plan. There was a roadmap, there were dates, there were rockets in development, and there was a powerful narrative. Humanity was going back, and this time to stay. But as we move through 2025, the story of lunar exploration is no longer a simple countdown to a single historic landing. Instead, it has become something far more complex and arguably more interesting. Today, we're going to explore how NASA and private companies are reshaping their plans for the moon, why timelines have shifted, what technical and political challenges are driving these changes, and what this all means for the future of humanity beyond Earth. To understand what's happening now, we need to briefly rewind. NASA's modern return to the moon effort is built around the Artemis program. Unlike the Apollo missions of the 1960s and 70s, Artemis was never just about planting a flag and leaving. The goal was sustainability, long-term presence, international partnerships, commercial involvement, and eventually using the moon as a stepping stone to Mars. The architecture of Artemis was ambitious from the beginning. It involved the Space Launch System rocket, the Orion spacecraft, a lunar space station called Gateway, commercial lunar landers developed by private companies, and a series of increasingly complex missions. Artemis I, Artemis E, Artemis E, and beyond. Artemis I flew and crewed around the moon and back, successfully testing the Orion spacecraft and the massive SLS rocket. Artemis E is planned to carry astronauts on a lunar flyby. Artemis E is supposed to land astronauts near the lunar South Pole, a region of intense interest because of suspected water ice deposits in permanently shadowed craters. But as of 2025, the timeline has shifted. Artemis E has been pushed back, and the overall architecture has been refined and, in some cases, reconsidered. Why? There are several major factors driving this recalibration. First, there is the technical complexity. The Artemis program relies on multiple new systems working together in a way that has never been done before. The Space Launch System is one of the most powerful rockets ever built, but it is also expensive and slow to produce. Orion must support astronauts on deep space missions lasting weeks. The Gateway space station has to be assembled in lunar orbit, and perhaps most challenging of all, the Human Landing System, the vehicle that actually takes astronauts from lunar orbit down to the surface and back, must be safe, reliable, and capable of operating in extreme conditions. NASA selected SpaceX to develop the first human landing system. Instead of a small, purpose-built lunar lander like those used in Apollo, SpaceX proposed a version of its massive Starship vehicle. This decision marked a dramatic shift. The moon landing vehicle would be based on a fully reusable, next-generation spacecraft originally designed for Mars, but integrating Starship into Artemis requires something unprecedented: orbital refueling at scale. The lunar version of Starship must be filled with propellant in Earth orbit before heading to the moon. That means launching multiple tanker versions of Starship, transferring cryogenic fuel in space, and coordinating complex operations before the crew even begins their journey. Orbital refueling has never been done at this scale, and it introduces new technical risks and scheduling uncertainties. Delays in Starship testing and development ripple directly into Artemis timelines. Meanwhile, other private companies are also involved. Blue Origin, led by Jeff Bezos, is developing its own lunar lander under a later contract. This creates a multi-provider model. NASA wants redundancy and competition, but it also adds layers of coordination, funding considerations, and development timelines. Another key element is the Gateway space station. Originally, Gateway was envisioned as a critical staging point in lunar orbit, a place where astronauts could dock, transfer to a lander, and potentially live for extended periods. Over time, NASA has adjusted how essential Gateway is for early missions. There have been discussions about whether some Artemis landings could proceed with minimal Gateway involvement, especially if doing so simplifies the architecture. This reflects a broader trend: flexibility. In the early promotional phase, Artemis was presented with bold target dates. As reality set in, supply chain constraints, budget negotiations, testing setbacks, NASA has moved toward a more incremental, risk-aware approach. Rather than rushing to meet symbolic deadlines, the agency is emphasizing system validation, integrated testing, and long-term sustainability. Funding also plays a significant role. Artemis is expensive. The Space Launch System alone costs billions per launch when factoring in development and production. Orion is similarly costly. In an era of competing national priorities and tight federal budgets, NASA must continually justify its expenditures to Congress. At the same time, the rise of commercial space has reshaped expectations. Companies like SpaceX have demonstrated rapid iteration, reusable rockets, and lower launch costs. This has put pressure on traditional cost-plus government contracts. As a result, NASA has leaned more heavily into fixed-price contracts for certain elements, particularly commercial landers and cargo delivery to the lunar surface. This shift represents a philosophical change. Instead of NASA owning and operating every major component, it increasingly acts as a customer, purchasing services from private providers. But that approach comes with trade-offs. Private companies move fast, but they also follow their own internal priorities. SpaceX, for example, is deeply focused on Starship as a Mars vehicle. Lunar missions are part of that roadmap, but not the only objective. Aligning commercial timelines with government mission requirements is an ongoing negotiation. International dynamics also influence lunar planning. The Artemis Accords, a framework for peaceful and cooperative exploration, have been signed by numerous countries. International partners are contributing hardware and expertise to Gateway and other elements. Europe, Japan, and Canada all have roles in the broader architecture. At the same time, China is developing its own lunar exploration program, with plans for a crewed landing and a joint international lunar research station with Russia. This creates a subtle geopolitical dimension. The moon is once again a stage for strategic competition, though this time it is framed as collaboration versus alternative blocks. Rather than a direct Cold War-style race, NASA must balance speed with safety, innovation with reliability, and competition with cooperation. Another major factor reshaping lunar plans is the focus on the lunar South Pole. Unlike Apollo, which landed near the equator, Artemis targets regions with extreme lighting conditions, rugged terrain, and deep-shadowed craters. These areas are scientifically rich but operationally challenging. Temperatures can swing dramatically. Communications can be intermittent. Landing precision must be far greater. Developing landers and surface systems capable of operating there adds complexity. Spacesuits, power systems, mobility platforms, all must be redesigned for longer stays and harsher conditions. NASA is also investing in commercial lunar payload services, contracting private companies to deliver scientific instruments and technology demonstrations to the moon ahead of crewed missions. Some of these robotic missions have faced setbacks. Landings on the moon remain difficult, and failures are part of the process. But these missions are essential for scouting terrain, testing technologies, and gathering data about resources like water ice. All of this feeds back into crewed mission planning. Instead of a single dramatic landing, the return to the moon now looks more like a phased campaign. First, validate heavy-lift launch, then test crew systems in deep space, then demonstrate large-scale in-space refueling, then execute uncrewed lunar lander tests, then attempt a crewed landing, then build up infrastructure. This layered approach inevitably stretches timelines. However, there is a deeper strategic shift underway. The moon is no longer just a destination, it is being treated as infrastructure. The long-term vision includes power generation, surface habitats, resource extraction experiments, and possibly manufacturing. Water ice could be processed into drinking water, breathable oxygen, and rocket propellant. If that becomes viable, the moon could serve as a refueling depot for deeper space missions. In this context, delays are not necessarily failures. They are adjustments in a multi-decade project. Private companies are also reshaping what going to the moon means. SpaceX envisions Starship as fully reusable, capable of carrying large cargo loads and potentially dozens of people. If that system matures, it could dramatically reduce the cost per kilogram to the lunar surface. That would open opportunities not only for NASA but for commercial ventures, tourism, research stations, even media projects. Blue Origin has articulated a vision of millions of people living and working in space. With heavy industry moved off Earth, the moon could be an early proving ground for such ambitions. Meanwhile, smaller startups are targeting niche roles: lunar communications networks, navigation services, resource prospecting, autonomous construction robots. The lunar economy, while still theoretical, is becoming a subject of serious planning. As of early 2025, the overall picture is this: the first Artemis crewed landing has slipped beyond its original target, but development continues across multiple fronts. Starship test flights are expanding capabilities, Orion systems are being refined, Gateway modules are under construction. Commercial landers are preparing for additional robotic missions. The narrative has shifted from when is the exact landing date to how do we build a sustainable system that can survive political cycles, technical setbacks, and economic fluctuations. This may ultimately be healthier. The Apollo program succeeded spectacularly, but it was short-lived. Once the geopolitical urgency faded, funding declined, and lunar missions ended. Artemis is attempting something more durable, a blended public-private ecosystem with international buy-in and commercial incentives. That kind of ecosystem takes time to mature. It also requires a cultural shift within space agencies. NASA engineers and managers must collaborate closely with companies that operate at startup speed. Risk tolerance must be recalibrated. Communication with the public must be transparent about setbacks without undermining confidence. For viewers and space enthusiasts, the shifting timelines can be frustrating. The dream of watching astronauts step onto the lunar South Pole in the near future feels tantalizingly close, yet perpetually just out of reach. But in many ways, this period of adjustment is a sign that lunar exploration is no longer a one-off stunt. It is becoming a system. The coming years will likely see uncrewed demonstrations of large-scale orbital refueling, further robotic missions to the lunar surface, incremental assembly of Gateway, and continued debate in Washington over budgets and priorities. If these pieces come together, the first Artemis landing will not be an endpoint. It will be the opening chapter of a sustained human presence beyond low Earth orbit, and perhaps that is the real story of 2025. Not that the moon landing is delayed, but that returning to the moon has evolved from a race into a restructuring of how humanity explores space, with governments and private companies intertwined, ambitions scaled to decades rather than years, and the moon positioned not as a trophy, but as a proving ground for our future among the stars. During Apollo, NASA operated under immense political pressure. The mandate was clear: land a man on the moon and return him safely to Earth before the decade was out. That urgency justified extraordinary budgets and rapid decision-making. Today, the environment is different. There is competition. Yes, particularly with China's advancing lunar ambitions. But there is no single presidential deadline tied to national prestige in quite the same way. As a result, NASA has more room to prioritize long-term reliability over speed. This is one reason why integrated testing between systems has become so central. The agency is not just testing rockets or spacecraft in isolation, it is testing how they interact. How does Orion behave after weeks in deep space radiation? How do docking systems perform in lunar orbit? How will astronauts transfer between vehicles in high-latency communication conditions? Then there is the human landing system itself. The lunar variant of Starship represents a radical departure from traditional landers. It is tall, massive, and designed for reuse. Unlike Apollo's lunar module, which was purpose-built and disposable, this vehicle is intended to operate multiple times. That implies durability, maintainability, and the potential for scaling operations beyond a handful of missions. But it also means solving unprecedented engineering challenges. Cryogenic propellant management in orbit is one of the most difficult aspects. Liquid methane and liquid oxygen must be stored at extremely low temperatures, in microgravity and under thermal cycling from sunlight and shadow. Managing boil-off and ensuring stable transfer between tankers and the lunar lander is a complex problem. Multiple tanker launches must rendezvous precisely, and fueling operations must be reliable enough to support crewed missions. Every successful test flight reduces uncertainty, every anomaly adds lessons, and each iteration informs NASA's confidence in committing astronauts to that system. At the same time, NASA has been clear that it wants redundancy. That is why it selected an additional provider for a second human landing system. The idea is simple. If one system encounters delays or technical setbacks, another can carry the mission forward. This model mirrors what NASA has done in low Earth orbit with commercial crew providers. Redundancy increases resilience, but it also increases coordination demands. Interfaces must be standardized, safety requirements must be harmonized. Mission planning must account for different vehicle capabilities. Beyond the vehicles themselves, surface operations are driving major revisions in planning. The lunar South Pole is not a flat, well-lit plain. It is a region of steep slopes, deep craters, and complex illumination patterns. Some ridges may receive near-continuous sunlight, making them attractive for solar power installations. Nearby craters may contain water ice trapped in permanent shadow, where temperatures plunge to extreme lows. Landing near such terrain requires high-precision navigation. Autonomous hazard detection and avoidance systems must identify safe touchdown zones in real time. Surface mobility systems, rovers, potentially pressurized vehicles, must handle uneven ground and extreme cold. Spacesuits are also being redesigned. Unlike the Apollo suits, which were used for relatively short excursions, Artemis suits are intended for longer duration exploration. They must allow greater flexibility, improve dust resistance, and compatibility with extended stays. Lunar dust itself is a serious concern. It is sharp, abrasive, and electrostatically charged. During Apollo, it caused wear on seals and equipment and posed health concerns for astronauts. For a sustained presence, mitigation strategies must be far more robust. All of this adds layers to mission architecture. Instead of a short sortie, Artemis missions are being designed as building blocks. One mission may deploy surface power systems. Another may test in situ resource utilization technologies, systems that attempt to extract oxygen from lunar regolith or process water ice. Later missions may assemble habitats or expand infrastructure. This incremental buildup changes how success is defined. Success is no longer just astronauts stepping onto the surface. It is demonstrating that systems can operate repeatedly, that supply chains can be maintained, that hardware can survive lunar night cycles, and that costs can be controlled. Cost control is perhaps the most sensitive issue. The Space Launch System has faced criticism for its hyperlaunch price. Supporters argue that it provides unmatched lift capability and reliability. Critics point to commercial alternatives that promise lower costs through reusability. In response, NASA has explored ways to integrate more commercial launch capacity into the broader lunar ecosystem. Even if SLS remains central for certain crewed missions, cargo delivery, refueling flights, and infrastructure deployment could increasingly rely on commercial heavy-lift rockets. This diversification reduces dependence on a single system and potentially lowers overall program costs, but it also requires careful orchestration of launch windows, orbital mechanics, and logistics chains. Another strategic evolution is the role of data and autonomy. Future lunar missions will rely heavily on autonomous systems. Communication delays between Earth and the Moon, while short compared to Mars, are still significant enough to limit real-time control. Landing systems must make split-second decisions. Surface robots must navigate independently. Resource extraction experiments must adjust to local conditions without constant human intervention. Artificial intelligence and advanced simulation tools are being integrated into planning and operations. Digital twins of spacecraft and habitats allow engineers to model wear, stress, and failure modes before they occur. This predictive approach is essential for long-duration missions. International cooperation also continues to shape the program. Partners are contributing modules, robotics, and scientific instruments. This spreads cost and risk, but it also ties Artemis to broader diplomatic relationships. Shifts in international politics can influence timelines and commitments. Meanwhile, China's parallel efforts add urgency. The prospect of multiple nations establishing footholds near valuable lunar South Pole resources raises questions about coordination, traffic management, and norms of behavior. While the Artemis Accords outline principles for peaceful exploration, their practical implementation will be tested as activity increases. In this environment, NASA's recalibration appears less like hesitation and more like strategic pacing. Rushing a landing only to encounter major setbacks could undermine public and political support. Demonstrating steady, incremental progress, even if slower than initially advertised, may build a stronger foundation. For private companies, the Moon is both a proving ground and a business opportunity. A successful large-scale reusable lander could unlock markets beyond government contracts. Scientific institutions, foreign governments, and even private research entities may seek lunar access. Communications satellites in lunar orbit, navigation constellations, and surface data networks could become commercial services. However, none of this materializes without sustained demand. In the near term, NASA remains the anchor customer. That gives the agency significant influence over standards and requirements. As we look ahead from early 2025, several key milestones will shape the narrative. Demonstrations of large-scale orbital refueling will be critical. Uncrewed lunar lander test flights must validate descent and ascent profiles. Continued progress on gateway modules will determine how central that station becomes to early missions. and congressional budget decisions will influence the pace of everything. If these elements align, the first crewed Artemis landing will mark not just a return, but a transition from exploration as spectacle to exploration as infrastructure, a transition from single-agency dominance to a hybrid public-private ecosystem, a transition from short-term geopolitical urgency to long-term strategic presence. In that sense, the shifting plans are not signs of failure. They are symptoms of ambition colliding with reality and adapting. Space exploration has always required adaptation. The difference now is scale. The systems being developed are larger, more interconnected, and more commercially integrated than anything attempted before. So when we talk about NASA and private companies revising lunar plans in 2025, we are really talking about something bigger, the maturation of a new model for go and beyond Earth. The moon is no longer just the next step. It is the testbed for how humanity will expand into the solar system, and that story is still unfolding.